We good for me to hop in? Cool. Sweet. Let me share my screen. All right. Can you all see my screen? Does everything look good? Cool. Sweet. All right. Dope. Yeah, so I was thinking we'd do like a Gnosis, like a safe deep dive, just to like inspire some of the hacking that we can all do together. I peeled back into the safe contracts recently and found that there was like a lot more there that I never really knew about. So yeah, I would love to just like share a whole bunch of like underlying Solidity stuff, like learning about safe and the way that things work at a low level really kind of helped me like understand more like of how Gnosis worked. I mean, it's like a critical part of the ecosystem for Ethereum for sure. I would say like on the level of Uniswap in terms of like public good and critical infrastructure. But yeah, lot to learn here. Contracts are pretty complex, I guess, from a beginner standpoint. So we've done a few things to kind of crack them back, and we'll learn a good amount together. Also, is everything sounding good? Like screen quality, like audio quality. Is everything all right? Sweet. All right. Cool. Cool. Sounds good. Yeah, so a little bit about me. I'm a smart contract dev for a local project called Bulla Network. Um, it's like an interesting like accounting protocol, but we built like a payroll payments and like invoicing platform, and we have like a Gnosis integration. We're looking at rolling out like a DAO integration before ETH Denver, but yeah, that's kind of how I started getting into a lot of this stuff is through that integration. I also teach like a Solidity deep dive meetup here in town, here in Denver, and we meet like at least once a month. We're doing one tonight actually, so if you're around, come through. We're doing like a end of year like CTF, where we just kind of hack on a whole bunch of stuff. And I've got like links here for my GitHub, my Twitter, and then like all the streams that we've done in the past for some of the Solidity deep dives. And so for this talk, I'm gonna drop the repo link in the DAO House chat. But I've done a few things that can help us. Here we go. Cool. So there's a repo that I've prepared for this chat, and I'll open that up in a minute. But yeah, so just I guess like on the agenda, we'll talk about like real quick like what can Safe do for those who aren't familiar, like the Safe ecosystem, and then do like a deep dive on the contracts to kind of understand like the different types of contracts in like which contracts reside at which addresses, and because it's kind of a complex like intermingling of different contracts, and so like I hope to just kind of lay things out for you a little bit to demystify how all these pieces interact together. Yeah, so I guess just to hop right in, like let's talk about like a safe real quick. So a safe can execute any kind of arbitrary transaction, either to other contracts or to itself. It can kind of generate these like valid EIP 1271 signatures. So like, you know, when you are doing something on chain, whether it's like a login or like a, OpenSea authorization to sell, or like, you know, you're signing something with your wallet to like, verify that you want to post it on Substack, you're taking your self-sovereign wallet identity and you are almost like consenting to information that's presented within that wallet. And Gnosis safes can actually do the same thing as well. You can kind of sign against any kind of arbitrary data, and whether that data is executed on chain or is expressed as a signature, Gnosis safe is really flexible. It's really flexible in like the way that it can validate like signature schemes. So like it can validate EOA signatures via like the ETH sign algorithm, EIP 712, and like I said, like EIP 1271 signatures. So you can have Gnosis safes, which are signers on Gnosis safes, and like it can kind of cascade endlessly. A safe can, like, in addition to like in addition to like executing transactions and signing messages, can also like refund transaction executors. You can install modules that bypass signature validation, and install guards that perform like checks and interactions after every transaction. So that's a little bit about what it does. This is the Gnosis Safe ecosystem, and from here I also would maybe I guess I didn't say this in the beginning, but I guess it's the point of this talk to kind of start really wide and then go down deep into code. But here's the ecosystem of the smart contracts. So I'll walk you guys through this, but so essentially when you go and you create, like starting from the left and moving to the right, when you go onto the Safe UI and you create your own Gnosis Safe, you're interacting with the Safe proxy factory here, which will create you a Gnosis Safe proxy. This Gnosis Safe proxy, this is like what you would consider to be like your safe address, right? So like when you send someone an address of your Gnosis Safe, it's actually the code that exists at that address is this little proxy contract. And the reason why we kind of have this little pattern is because the Gnosis Safe and Gnosis Safe L2 logic is really dense. It's a massive contract, so it would cost you like a couple ETH to deploy a Gnosis Safe every single time if you wanted to copy the logic every single time. But this pattern allows you to just kind of to get your own storage, right? To have your own safe and set it up with whatever kind of owners and signers you want. But it will actually look up to what's called the master copy to get its logic. In addition, every safe is called with every safe that's like deployed through the Safe UI is also deployed with like a compatibility fallback handler. We'll go through that as well. And then there are also some utility contracts in the ecosystem, like the multisend, which allows for a safe to execute like n amount of transactions at once. And then multisend call only, which is just like a safety version that kind of allows you to that only allows these calls to be external calls, not delegate calls, which means that like the safe couldn't modify its own storage in a sense. There's also safe plugins too. So here in this category you have modules, modifiers, and guards as well. So yeah, that was just like, I guess, kind of my introductory overview. Next, I'm gonna kind of walk through the code in terms of like the life cycle, so like setup and execution and stuff like that. But before we move on, yeah, I just wanted to see if there are like any initial questions or any thoughts. Yeah, so that's a great question. So there are two types of calls in the EVM. There's one that's called it's just call, and another one that's called delegate call. Delegate call allows another contract to it allows the contract that is receiving the call to modify the caller's storage. So like you could imagine, right? Like if Gnosis Safe made a delegate call to some other contract here, then that delegate call could update the Gnosis Safe storage. Like, for example, like the signers, right? So if I made an unsafe delegate call, it could delete all the signers that I have on my safe, or put the threshold at 100 when I only have like 2 signers, right? So it could brick my safe or transfer tokens or do something crazy. Whereas just like a call um, takes, my safe would make a call to another contract, and then that contract would just, uh, I guess, execute as normal. Right. Exactly. Yeah, delegate call is really powerful, but it is to be trusted, right? Um, Yeah, yeah. So I don't know if that helps, right? Like when I make a normal transaction with my EOA wallet, like my hardware wallet or my MetaMask, that's going to be a call, right? But smart contracts have the ability to make this special type of call called a delegate call, and they have the ability to make static calls too, which is like a view only. So like kind of has extra protection that says like, hey, this call should only view. It should not modify storage in any way. Yeah. Any other questions? Cool. Sweet. So yeah, since this is like a code deep dive and slides can get kind of boring, the slides are mostly like a reference for you in the future. This whole talk, for the most part, is supposed to be like a talk that will allow you to. It's meant to be a reference at any time. Like I found that there was a lot of issues, not issues, just obstacles when I needed to go and reference contracts in like the Gnosis safe ecosystem. It was like really difficult to figure out like what was doing what and what contracts were where. So like I hope that this is like a good like mental model for like what the contracts do and don't do. And so that being said, I made like this repo where I condensed the kind of the two important contracts into just two files. So like, for example, I don't know if you ever have tried to go look at the Gnosis Safe contracts. Here they are here. It's pretty complex, mostly because inheritance, right? So I don't know about you guys, but I'm just like, I'm very, very visual. So it's difficult for me to like understand this inheritance tree. And like, I'm much more of a fan of flat contracts, right? Because you have this contract, Gnosis Safe, which kind of inherits from all these, which will, inherit from other contracts itself as well. So you kind of have this like cascading tree of like unknowns. This especially gets difficult if you've ever worked with like storage slots because, inheritance, like maybe the first slot, the first thing that's being stored on the contract is buried deep in inheritance. So what I did is I created this contract here. It's called Flat Safe, where basically I took through, and we'll just run through it real quick, just to give you like a 40,000 foot view. But if I go in my editor and I say fold all, this will give us like a nice flat version of the contracts. So these are just two interfaces that it uses, and then like an enum. I abstracted out all the constants that are used across Gnosis Safe, and we'll talk about those. I made a flat safe contract and a compatibility fallback handler contract. And so if we look at the flat safe, it starts from the top. And so this is kind of like supposed to be your reference file for Gnosis Safe. Any sort of like storage value or function call, I ended up putting like a little tag here to say like what file they're in. And I've removed and cut down a lot of these comments. So you'll see like, if you're going through and you want to see like what the different functions are and how they work, I've ordered the contract to put all the storage up front. So this is the storage part of the smart contract, the constructor, of course, all the events in the smart contract are at the top, and then I have it organized by write functions and then read functions. So if you ever wanted to come in here and like reference like, okay, what does the setup function do? What does the exec transaction from module function do? Then you can hop in, you can like do a Control F, hop to that part in code, see what it does in line. And then if you ever need like more visibility on what it's doing, or you want like the dev comments or the nat spec, you can just like pop open like module manager and go in directly and find the function and sort of like have everything be opened up for you. So yeah, I guess so. These are all the read functions here, and then the write functions at the top, the read functions at the bottom. Gnosis, it makes sense why they split everything up. It is pretty huge. There are a ton of functions, and then the compatibility fallback handler just has a few things here as well. So yeah, this is going to be like a little bit, I guess, more of like a intermediate level Solidity deep dive, but like please stop me at any time if something doesn't make sense, and we can all learn something together. I'm sure like if you have a question, then you're not the only person in the room with that question. So we'll start here with just like the setup call to figure out some different things that we could do if we wanted to program in some like cool functionality with like vaults in terms of like DAO house or like like Moloch DAOs, since safes are being used as the vault, and Deacon can I know more about the safe contracts than I know about the Moloch contracts, but so Deacon could probably fill in my gaps in knowledge as we roll through this. But yeah, let's start with the setup function. So the setup function is like it's going to be the entry point for every single safe. So when you go and deploy I'll show you just like from a high level transaction point of view. When you deploy a safe on the safe UI, you're interacting with this contract here called the safe proxy factory. And when you create a valid transaction to that safe proxy factory, you call, you're deploying your own little proxy, which is like you're deploying your own Gnosis safe, and then you actually call the setup function on that Gnosis safe. So I can like open this in Tenderly, and we can see what happens here. So if you see this factory will call the setup function for us, which will then set up the owners, set up any modules that we want to specify, and set the internal fallback handler as well. So like, for example, like I guess you could see here's the input. So like this is just a transaction I grabbed, but we specify the owner's threshold, any sort of like init callback data. And I did just pull this open because I wanted to make a note that anything deployed through the safe UI does have this fallback handler. We can look at that in a little bit, but that fallback handler ensures that like the safes can actually receive NFTs. So it's how 1.3.0 Gnosis safes are compatible with versions below it, and also it makes it compatible with like the on ERC 721 received and on ERC 1155 received functions are called back to when those tokens are being transferred. So I was actually using like a product like a year ago. I think it was like Parcel or CoinShift, like way back in the day, like in their beta or something like that, and they weren't deploying with a fallback handler, so like their safes couldn't actually receive NFTs. They would revert every time you try to send an NFT to that like kind of treasury address. So this is pretty dang important, is to have that fallback handler there. So this is what the setup function looks like. It sets up the owners with the threshold. So I'll pass 3 owners, with a 2 as the threshold. That'll be like a 2 or 3 safe. And then also interestingly enough here, this is like kind of where the customization piece comes in. We've got a 2 and a data field. So if we look at how this works and we open up this setup function, let's see. So setup modules is called with 2 and data. So if we go to the setup modules function, what it will do is it will actually execute it'll execute a delegate call to the to contract, um, with kind of the remaining gas with just the data field. So what we could do, we'll talk on the next slide about like some of the cool like functionality that you could build like customized into this, but we could kind of create our own smart contract that will set like special initialization parameters for a safe if we wanted to kind of hack on something. And that would allow you to create a safe and set it up any way you want, in one transaction, which would be pretty neat. So any kind of like, since this is a delegate call, we could create any contract that would like modify the storage of this safe and set it up all in one sort of atomic transaction. It sets the fallback handler, which we talked about, and it can arbitrarily modify its own storage by making a delegate call to the to param with the data param. We just talked about that as well. It can also refund a payment receiver as well. So you could, I guess you could pay someone for deploying this safe in payment. So the payment param is in way, and that will be refunded to the payment receiver in the payment token. So if the payment token is like all zeros, then the safe will consider that to be ETH, and if the payment token is like a token address, then it will try to like transfer that token. There are a few like interesting things that we could do with the setup function. So like you could set up custom modules, you could set up like a transaction guard on initialization. You could I could imagine you could pre-approve an amount of transactions to be executed, so you could like almost like preload your safe with transactions for anyone to kind of come in and just like trigger an execution on. Something interesting, I know this has been jammed on a little bit, but you could also spin up like a single use DAO, there's like a timer on initialization, so like the DAO could be like, or like the safe could be self-destructed after a certain amount of time, if like some sort of like on-chain parameters aren't met. There's also like, you could just really execute any kind of arbitrary transaction or callback on initialization. So really kind of like the point here is like the world is your oyster. You could do some like really cool, you could kind of make your own flavors of safes just by having like, from a UI specifying a call from the factory to say like, hey, make this type of safe every time. And all these features would need to be written into a smart contract that would be deployed at a fixed address, and then you would pass that as the to address in the here in the setup function. So you would kind of like write your own custom code for like what a setup would look like, and then you'd specify that deployed contract here into. So Deacon, I don't know if what does DAO House do for the setup? Do you guys use a callback? Do you guys use like this to in the data field to set up these vaults? Mm. Yeah, no, that's cool. That's how you program all that super custom stuff. Yeah, what Deacon is mentioning here is with like the determined address is you can you know, if you looked at the ether scan, this is just like everyone coming off of the safe UI is calling create proxy with nonce here, which allows you to specify a specific salt. That salt is to, you know, if the salt and the initializer are the same, the address of the deployed safe will be the same as well. So it's what's called like deterministic, right? So you can calculate that like off chain, and then you know, deploy it based on the initializer. This is also, like, side note, this is also how you can get safes with the same address across different chains. And that's like kind of one common pitfall that you can do when like doing anything with smart contracts or even front end, is like assuming that that you know, I guess, like, you know, you and I are EOAs, they're controlled by private keys, so it doesn't matter which chain we're on. But like, for example, like if I deploy my Gnosis safe only on one chain, but I'm assuming that it's on all chains, anyone can go in and change the salt nonce, or I guess use the same salt nonce in the initializer here, and can get the same safe address. So like, I think this was like related to the Wintermute hack, if I'm correct, is that like they had a safe on one chain, but they ended up someone else used like, and they sent funds that was meant for that safe, but on the wrong chain, and then someone deployed a Gnosis safe with that same address and like was able to like grab the funds. I'm pretty sure that's how that one went, but yeah, there's all sorts of fun stuff that you can do. You can figure out the address of your safe before you deploy it. Side note here, I combined the Gnosis Safe proxies, Gnosis Safe proxy factory, and the iProxy creation callback files into this one file here, a safe creator. So this is like what creates the safe, and then this is like all the functions that exist on a safe at a given time. Cool. Okay, yeah, so any questions about like the setup function or some of the stuff that you can do? It's pretty straightforward. It sets up the owners, sets the fallback handler, sets up the modules, pays anyone if you want to refund them. Cool. All right, sweet. So now we'll go to like, I guess, the second part of the life cycle, which is like executing transactions. So first of all, this is the internal function called, oh, here we go. Yep. So this is the internal function called execute. This is like how a Gnosis safe actually like executes the transaction itself. So this is internal. It can only be called by the safe itself. It returns the success if it works, and it just switches across the operation. So if the operation is listed as a delegate call, it's going to delegate call to address with the forwarding the amount of gas. Otherwise, it's going to just send a call. So that's kind of how this works. So all the following execute functions will use this underlying execute function, and you can specify like a certain amount of gas here as well. But here is the exec. I'm gonna unfold all these. Actually, this is a pain. Unfold. So here's the exec transaction function. So there's going to be kind of like three things that happens. You have all these. You have the value, the data, the operation, the gas, the base gas, the gas price, gas token, and a refund receiver. And that's kind of all the transaction info, and we'll talk a little bit about this, but really this function kind of does three things from a high level. Is it encodes the transaction data, it checks if the signatures are valid that you pass in, so that you signed, you know, n out of m times against whatever transaction you're trying to execute. It will then see if you have any guard initialized, and then like ask the guard if this transaction is okay. It will then execute this transaction, and then it will refund the refund receiver if there is any, and then it will ask the guard again if there is one, if the transaction is okay after the execution as well. So I did some work on the slides here to just talk like a little bit about this, like transaction coding specifically. So like we saw in the safe transaction that there's this like two value data operation, base gas, kind of all these different things. And so like I mentioned in the first slide that safes have their own method, their own algorithm for like encoding transactions. And also for encoding signatures. So this is kind of based off of how EOAs or externally owned accounts like our wallets handle the exact same thing. So in terms of it like an EOA, each transaction, you take all the data in the transaction that you want to populate on the blockchain, you RLP encode it and then hash it to a bytes 32 value, and then you sign it with your private key. And then when you present that sort of like transaction with the signature to an Ethereum node and it's like broadcasted, it can validate that like you with your EOA sort of like signed consent for that signature to happen, right? So if you look, these are really, really similar, right? That like if you have to sign all these things to make sure that your transaction can't be used maliciously or on a different chain or at a different time, or so it's like there are all these things encoded into the transaction data that means that like you can only execute this transaction, that the signature is only valid on one chain one time, and it's going to be the exact same with like a SafeTX, but it's a little bit different. So it's encoded, just like for you to know, for reference, it's encoded to the AIP 712 spec. It's Kachak 256 hashed, and then assigned by EOA. So there are a few different things on the SafeTX. Like for example, there's going to be like a refund receiver and a gas token, and an operation. That's kind of what sets it apart from like an EOA transaction. But it's still going to have like the from, which is sort of like the safe address, like the from to sort of values. And so yeah, it's I guess the TLDR is that like the transaction is kind of has its own method of encoding. And if you're interested in this, it is this encode transaction data function is how this works. So it takes kind of all these different things, all the different inputs, the value, the data, the operation, the gas, all that stuff, and then the current nonce of the safe, which just means how many transactions the safe is executed. It like concatenates them all together with what's called a type hash. That type hash is simply just like a specification based on EIP 712. And then it kind of hashes it together in its own sort of like, it hashes it against the domain separator, which means that like it can only be used for this safe on this chain. So it seems kind of complicated and maybe even trivial, but it's super important to make sure that like when you sign a transaction that like you're okay for a safe transaction to execute, it can only be executed on that safe for that nonce on that chain. Yeah, so next we'll go into like signature verification. Signature verification. So if we go back to exec transaction. So we get the kind of in the same way in which like our EOA works, right? We get the transaction hash data. So this is like kind of the safe Gnosis safe domain specific version of a transaction hash. And then you check the signatures, and this is kind of where like the signatures are checked. So we pass an array of signatures in. So if we go to the check signatures function, it's going to check the signatures against the threshold. So this is the check and signatures method. This is probably the most complex function in the whole file, but it's really freaking cool. And there's a lot of stuff here that I didn't know about at first. And we can run through that real quick. So it takes in the transaction hash, and then any kind of data, an array of signatures, and then the amount of the required signer. So that's like the threshold, right? So you'll see here there are three branches. Well, actually, yeah, one, two, three, four. So there are four branches for how signatures can actually be encoded, which is interesting. So normally in Ethereum, like a signature kind of looks like this. It's like, you know, bytes memory. Signature is going to be the ABI encoding. It's going to be encode packed, and then it's going to be like a 32 bytes. I think it's R value first, and then a bytes 32 V. RSV, I forget which one. Oh yeah, R, yeah, V is uint 8. All right, so it's gonna be S, and then a uint 8, like a single byte V value, and that is like a ECDSA signature scheme. So you need these three values to basically prove that an address has signed off on something. And so what they do is, in the case of Gnosis Safe, is they encode like different algorithms, I'd say, like signature algorithms based on like into the V value. So like for example, you could you could put encode into the V value. You could say 0 for like a smart contract signature, and so like. Yeah, there's a couple different ways of encoding things. So like if, and luckily like the Safe SDK handles all of this for you, so you wouldn't ever have to think about this. But it's just like, I think it's an interesting learn. So if the V value is 0, then what it's going to do is it's going to get the current. It's going to assume that you encode the owner address into the R value. And then it will call this is a EIP 1271 signature verification. So it's actually going to make a smart contract call to say like, hey, is this a valid signature? So like if you wanted to understand more about this, you can go and read the EIP 712 spec. It's basically just kind of like asks a contract if a signature is valid instead of, and it allows like smart contracts to sign off on transactions. Next, if the signature is 1, then it's what's called an approved hash. Approved hashes are really cool. Normally, how Gnosis Safe works is it collects all the signatures off-chain and then submits them on-chain, but that does create like a central point of failure if like what's called the safe transaction service ever went down, because it's just a server. But what you could do is there's a function on here called approve hash. And so you would get the safe transaction hash, and you would call this directly with your EOA account, and you would say, or with your smart contract wallet, and you would say, hey, approve this hash. And so it's a way that you can go in as a signer on the safe and just kind of like manually approve stuff to make sure that that your transaction could be signed off on without the safe transaction service. Because you would need some sort of server to kind of bundle up all those signatures off-chain and then submit them all at once. But this is a way in which you can kind of do them incrementally on-chain in a way that's also discrete too, because it's hashed, so no one knows what kind of all the signers are signing off on incrementally. Next, also if the V value is greater than 30. Then it's going to be the Ethereum signed message algorithm, which is like, I guess there's two ways of, I'm sure you've seen, like if you're doing an order on OpenSea, right, you kind of get that signed typed data. It's like a really nice field, or I guess it just like shows in your wallet kind of each like parameter in like a JSON structure. The more primitive version is just like Ethereum signed message, which is like, I will sign this message kind of stuff. I think it's the difference between like, let's see, I have the playground here, but there's like No, never mind. I think I lost it. But there was an MetaMask has like a really nice um, endpoint. That's a shoot. Anyway, oh yeah, here it is. Um, so like, yeah, for example, right, like uh, the EIP, the yeah. So this is personal sign, right? This would be like me signing a message where it's just like a string that kind of comes through in my wallet, and this is what sign type data looks like, where it's like kind of nice and formatted for me. And if you've ever used Gnosis Safe before, like this is what this looks like. So it has like backwards compatibility for all these different types of data. Uh, I mean, all these different types of like signing algorithms. Um, and then like this is going to be the flow for EIP 712. Which is just sort of like the standard flow, since the V value in that is like normally going to be like 27 or 28. So this kind of has like a lot to do with like the ECDSA signing algorithm, but just know that you can like, this is where you would encode like this is how you would encode signatures from different smart contract wallets. And then possibly my favorite piece of code from the whole repo is this line here, and it's a way for this algorithm is super cool. So like it's a way for you to basically if you're iterating across owners in an array, it's a way for you to protect yourself against duplicates or zero addresses, right? Like, so for example, this EC recover function will return a zero address if it will return address 0 if it fails. So if you say require that the current owner, so first of all, if you initialize last owner as address 0, and then if you require the current owner is greater than the last owner for every iteration, then you protect yourself against zero addresses, which means like failing signatures. But and then you memoize this kind of at the end of your loop. But also too, you prevent yourself against duplicates, right? So if like wallet ending in 8946 tried to like double sign for something, last owner and current owner would both be 0946, and this call would fail. So what you do is you have to do a little more extra work off chain to pass your signatures in a order ascending fashion, so that like address 1, like I guess the signatures are ordered from like address 1, address 2, address 3, address 4. And the like I said, the SDK has tools for this, so you don't have to think about it. But like if you're ever building something like this yourself, where you have to ensure like that there are no duplicate signers, I've used this algorithm before, and it's super efficient. It's really nice because you just do this check, you sort the signatures at the beginning, and then you can just do this current last owner check. Any thoughts on that before we get back to the code real quick? Yeah. 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 No. So funny enough, I've actually I found it in Miguel. I forget his last name. In the the Solidity kid with like the purple hair that everyone kind of knows on like Twitter, and I think he does stuff for WorldCoin too. But anyway, he wrote this like library called Little DeFi, or like Lil DeFi or something like that, and he had this contract called Lil Gnosis. And that's where I first, I guess, like saw the algorithm, where it was like, what you do is you memoize the last, you memoize the current verification, and then you check it sort of in this array loop, to prevent against duplicates. I think it kind of came about because like One, like I sort of had to write my own implementation for like kind of uh, I guess almost like an owner-bound vault system where like I had like an array of owners that protected a certain token, and so like you had to see if they all signed off on it. So it was mostly from like me building some of this myself. Um, but then also like, yeah, seeing that little Gnosis library and being like, oh, I actually thought it was his algorithm. And then I came here and then like looked at this myself because, yeah, I mean, that's kind of the point of this deep dive too, is that like the safe's code is like so optimized. It can be like really thick to get through and like understand like what every line is doing. Super imperative. Yeah. Sweet. Cool. Yeah, so yeah, mostly just getting in here and getting my hands dirty. It's kind of brutal, but that's why I try to make this like contract as flat and like easy to sort of navigate as possible, so you don't have to jump between files and lose your place. Yeah, so that's check signatures, right? Like we expect this to revert. So if we get this far, it means that the signatures are all good. Then we ask the guard to check the transaction. Guards are cool. There's this kind of it's maybe not a misnomer, but it's just like it says check transaction, but actually you could do something way more arbitrary with a guard. Like there's some cool guard ideas that we could jam on for sure, where like especially related to ball and like and vaults, you could do something interesting where like you actually make a call back to the ball contract every single time that you execute something from the safe, right? Like this is just forwarding execution to the guard. So essentially you could do anything in this transaction that you wanted to. What it's intended to do is it's intended for you to do just like a check where you would revert, right? So it just delegates execution flow. Checks happen before and after execution. Guards are expected to revert if there's an issue. And then I also have some examples here too, right? Like this is from the safe contracts repo, but like there is a like reentrancy guard, which it'll check like if the if it's currently active, and then it will like revert if it's being like if the safe is being re-entered into. There's also like a delegate call transaction guard. You could take the data field, right? So like for example, in the contract, if the data here is some data to transfer some USDC, then you could create a like daily spend limit guard where you say, okay, like, hey, it's been, since this block timestamp, since 1,000 USDC was transferred, you've hit your daily limit, right? So there's a whole bunch of stuff that you can do in here with a guard, which is pretty cool. Some of it is actual guard stuff. Some of it is like you could just execute any arbitrary function based on whatever's being sent here, which is super neat. And it looks like it also passes message sender. Yeah, which is cool. So you could see like, you could have a guard that like only allows like technically anyone could execute this exec transaction function as long as they have passed the valid amount of signatures. You could check against the message sender and like ensure that it's only a certain address as well. So yeah, that's that part. That's guarding. Some interesting use cases there. And so now we kind of get into transaction execution. So it'll just like simply execute a call to another contract, delegate call, or a normal call. Like I said, I guess earlier I covered this before. So delegate calls can be dangerous because they modify the safe storage. But there's just a note here that like any kind of multi-send transaction does need to be a delegate call, because it does kind of need to be the safe doing something multiple times, not the multi-send contract doing something multiple times. And here's a little bit of a gotcha as well. You don't really need to worry about this. This is just like some gas shortcomings. There's an interesting article. This is related to EIP 150 an article that I could include explaining that. But here is a little got you. Um, so yeah, it's this line, right? So like execute won't fail, but it will return success, true or false. So this contract requires that the transaction execution is successful, or if the transaction gas listed in the transaction is not zero, or the gas price is not zero. So this is kind of weird, but normally when you and I submit like raw safe transactions, we're going to put safetyx gas is zero and gas price is zero, which means that like we're requiring this to successfully execute. You could theoretically cap the amount of gas that you want to have happen on a transaction, which will allow the underlying transaction to fail and kind of roll forward. So like, if you're doing something, I don't know, custom, and you said like, okay, like I only want to spend 1 million gas, right? Or I only want to spend as much gas as the safe can afford to refund, then you could specify safe transaction gas and gas price. And actually this call won't fail. It will just continue, but it will emit a success or failure event, which then gets picked up by the transaction service that shows in the front end like, hey, this failed. But the actual like underlying call won't revert is what I mean. So that's kind of another one of those got yous that happens here, is that like this call will fail unless you've specified transaction gas or a specific gas price. If you have specified a gas price, it's going to like this is how you handle like refunds. So you could have like program some sort of custom safe functionality where you select like a refund receiver, where you kind of have like maybe like a bounty for anyone to go execute a transaction when it becomes like I guess economically incentivized to. So yep, that's that. And then there's just that check after execution guard check as well. So that's a ton, but that's kind of where the magic happens in terms of like exec transaction. Any questions? Any questions on that side? That kind of like brings us to the end of like our life cycle questions, and I just have like a few other notes to like give you guys like ideas of stuff that you can build, because the rest is pretty straightforward once you get out of the transactions and the signer stuff. The rest is pretty like declarative, straightforward. Oh yeah. Sweet. Yeah, no, I've got time. Should only take like 10 more minutes, probably 10, 15. Sweet. Okay. So next is just like there are a couple different flavors of exec transaction here. One that's like exec transaction for module, and one that's exec transaction for module and return data. So that it's just the same version as this, but it just returns any sort of data that the module returned. So if you notice, like this bypasses the entire like crazy signing algorithms that happened up here in the guard checks. All it does is it calls execute. So for example, like if a module has access, it bypasses the guards, it bypasses the signing, and just has straight like execute access. So whenever you create a module, you got to be really careful that it's doing exactly what you say it is, because it can do anything to this safe. It's a true plugin. The only requirement is that the module is enabled, so it assumes that you are a module. You could theoretically allow your EOA, like your MetaMask wallet, to be a module here and do something, but that would kind of completely bypass why would you have a multi-sig wallet if your wallet is just like a module, so it can do whatever. But Yeah. Anyway, it'd be interesting maybe where like a use case where you have like a Gnosis-based social recovery where like your main wallet is actually a module, and then all your friends are signers, right, or something like that. There could be some interesting. There's an interesting use case there. Um, but yeah, like I said, I'll just skim through the rest of this stuff real quick because it's pretty straightforward. Um, Handle payment is just like it's a private function. It's an internal payment handler. Um, uh, this is a way for you to set the guard. So one safe can have one guard, to clarify, but one safe can have many modules. This is that internal setup modules function that is called at the beginning of the setup function. This is an enable module function for your safe to enable or disable a module. This is the setup owners call. Add owners with threshold, remove owner, just like owner management stuff. Transfer token. This is how token transfers are managed in a way that's like backwards compatible for non-ERC20 compliant tokens. You have set fallback handler methods, and then these are just kind of all your read functions, right? So you have read functions for check signatures, encoding transaction data, getting safe transaction hashes, seeing if modules are enabled. There's also an interesting method here for getting raw storage slot values. So like you could say like, get me the value at storage slot 0, storage slot 1, storage slot 2. That's some like big brain solidity stuff where you're thinking about like storage slots, but you could ask this contract like what the required amount of gas is for a certain transaction. You could do a simulation. This one required TX gas. Yeah, it's super weird. I don't know. Do you know why it does that? Wraps it in a string. Oh, right. Oh, yeah, I guess revert only takes well, yeah, it takes a string. Right. Interesting. That's super strange. So, huh. Yeah, I guess like if you don't get a return value. Oh, yeah. Oh, interesting. Yeah, I ran into some issues with this on Bola stuff because we were writing code for like a version 1.1 safe, and yeah, it was just super funky. But yeah, like I think literally how they handle it in the SDK is they call this function just like in a loop until it doesn't fail. They like keep incrementing the gas until like it works. Yeah, it's the most like ridiculous thing. Yeah. Yeah. No, it's true, man. Yeah, if you like F12 into the SDK, like if you just kind of like look at some of the functions back there, it just does it in a loop and like increments the gas by 20K every time. And then the one that doesn't revert, it like breaks the loop. It's like such ridiculous programming that you have to do for this stuff. Oh, like for like a refund? Mm. Yeah. So I think you could do that with a guard. Now that I'm thinking about it. So like, for example, you could create a contract. Okay, yeah. So here's what you could do, is you could either create a guard or like create a module, I think. And what your guard will do is it'll check that the person calling exec transaction is like this special tax contract, and you would have to route all your exec transaction calls through that like fee contract. And that would be a way in which you could sort of like make sure that no one can come to this contract and directly execute something with valid signatures, that they would have to route it through the fee contract first, and then that fee contract would just like ensure that like message value is a factor of like the current gas price, because like those values can be read on chain. Like I'm trying to look transfer token. There's where is it? Refund receiver. There's a refund receiver. Oh, handle payment. Yeah. So yeah, there's a tx.gas price that's available in any transaction. So you can see like, you could make sure that like the base gas, that it's like a factor of whatever gas price. Yeah, you could definitely do that. Yes. Yeah, right. Yeah, no, definitely possible. Um, yeah, no, that's a good question. That'd be neat. So last thing I want to mention is about like fallback handler, because this was the last sort of confusing piece for me. I think I've said this like so many times now. I didn't ever practice this talk before, so this is good practice. But yeah, when you deploy a safe, it's deployed with a fallback manager, like a fallback handler. This is called the compatibility fallback handler in the safe contracts. I included it at the bottom of my flat safe in a function. It's just called compatibility fallback handler. Oh wow, this slide is like totally messed up. But anyway, so I made this graph, not graph, but just like diagram. So when you make a call to Gnosis safe, where the function doesn't actually exist on that safe, it'll pass it to the fallback handler. And so this kind of says like, hey, let me find my fallback function. Yeah, so here we go. So what it'll do is all this mess of assembly, it will simply just like, it will forward your call along to the fallback handler. So what it allows for it kind of allows for like a sense of like upgradability on the on a safe, and backwards compatibility as well. So like as you see on the left, right, like if I call any of these functions on the left, those functions and the code to execute those functions exist on the Gnosis safe. But like if I call anything that doesn't exist on the Gnosis safe, it's going to forward it to the fallback handler. So like anything like is valid signature. So like, oh shoot, wait. Hello, can you guys hear me? Okay, cool. Sorry. Yeah, my headphones disconnected for a second. Technical difficulties. Anyway, yeah. So like EIP 1271 lookups, message hashing, token callbacks. Those are all specified on the fallback handler actually. So like kind of how the code works is it goes to the safe, doesn't find a matching piece of code, and then oh my gosh. Okay, I'm having more issues. But anyway, I think that makes sense. So I think I've explained it. So it passes those onto the fallback handler. So you could definitely write your own custom fallback handler that like kind of handles custom code at the safe level. to like intercept any kind of calls if you needed to do that. Yeah, so that's the fallback handler. You can kind of check those values out. So I've got some quick hits here just to like finish us off. So like, just so things that you should know about the ecosystem is like signatures are gathered up off chain and submitted all at once via the safe transaction service. You could estimate the amount of gas required to execute a transaction by recalling required TX gas. That's a function. If the safe transaction service ever goes down, you can manually sign transactions by calling get transaction hash, then calling approve hash with your signing wallet, calling get message hash for safe to encode a signed message for safe. So like in the same way that a site that like a EOA has both methods for encoding transactions and encoding like signatures, safe does the same as well. So that's the get message hash for safe call. Each safe is deployed via the safe UI. It's a proxy contract. I mentioned that, meaning its cost is minimal. And then if you're making modules, there's also a module factory to deploy new modules. Like the deploy cost, if you deploy via the module factory, is like astronomically lower. So would like always recommend that you do that. And then like something and then I just like kind of had some ideas like going through here, right? Like of things that maybe people like would want to jam on. So like, a contract can actually validate a safe's EIP 1271 signature given a sorted array of owner signatures over a threshold. So like all that jargon means that like normally with an EIP 1271 signature, like when the caller calls is valid signature, it will pass it'll pass the 32 byte hash and the signatures. But one thing that's cool about and normally you would have to actually like write to storage on chain to say like, okay, I'm like marking a certain I'm marking like a certain hash as signed by my smart contract wallet or by this wallet. The cool thing here is actually like this function delegates the call, like if the signatures are length is greater than 0, it delegates that whole call to the check signatures function, which is the same signing algorithm that's used for transactions. So what that means is, and I've got like example of this like kind of in the when I was like working around on the BOLA contracts, but that you could actually say that a safe has a valid signature based on off-chain signatures from a bunch of signers. So like I did this here in a test, like I got a digest, like a message digest by like I just like any kind of arbitrary EIP 712 digest, and then like I made sure that like Alice signed it and then Bob signed it, and then I concatenated the two, and then like actually I like what that does is you can use that signature that like you can concatenate all the owner signatures together and say that like a signature is valid on chain without the Gnosis safe having to write to any storage. So there's nothing like that, nothing for that in the safe UI, and I don't know if that makes sense, but I think there's some cool stuff that you could do with that to gather up like owner signatures offline. And then like there's also like a custom, you could write your own custom fallback handler that could be deployed to a custom function to implement custom function calls and custom storage rights. You could also install like a trusted guard that performs any action to like a ball module on every transaction as well. Yeah. Ooh. So that's everything I've got. It's kind of a deep dive. Hopefully like this talk can be saved for like a reference too, and you can like go through and reference this flat safe. Hopefully this will be useful for you as well to sort of just be able to like check through and see like what functions are actually available to call on a safe, how does the safe work, how are the storage slots organized, what's available via the compatibility fallback handler, like all the way down here, and then just explaining some of the black magic behind all the function calls. But yeah, I guess that's all I've got. So totally open for questions. I know that was like a really really long talk, so thanks for being patient. But yeah, hopefully that's helpful. Yeah. 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 I started making this like a week ago, and you were like, I guess I didn't. I guess I missed the fact that it was like 101. I was like, oh sweet, we could go like do like a deep dive on like a on safe or something like that. Yeah, this is about as hard as well, I mean, hard as it gets. Yeah. Right. Oh yeah. That's truly impossible. Yeah, yeah, of course. Absolutely, man. Yeah. Yeah, no, they've done a ton of work, and there's so much that's abstracted away. They do a lot to make your life easy.